A star begins as just a cloud of dust and gas called a nebula. These clouds can be classified into two groups, diffuse nebula and planetary nebula. The larger type, diffuse nebula, can lead to the formation of as many as 100,000 stars, each the size of our Sun. Turbulence at the centre of these clouds lead to knots with a significant enough mass to create a gravitational pull, meaning the cloud will collapse in on itself. As the cloud collapses, the material at the centre will heat up, leading to the core becoming a protostar. A protostar looks like a star, however its core is not at a sufficient temperature for fusion to take place. The luminosity from a protostar comes from the heat as it contracts. However, protostars are surrounded by dust, therefore they are hard to observe. After around 100,000 years, the protostar will stop growing and the surrounding material will be destroyed by radiation, at which point it will become a main sequence star. A main sequence star fuses hydrogen atoms to form helium atoms, continuing to do so until it runs out of hydrogen, at which point it will fuse other elements. The lifespan of a star depends on its size, as it will have more hydrogen to fuse. The size of these stars can range massively, from OGLE TR122b, which is about 12% of the size of our Sun, to R136A1, which is 265 times the mass of our Sun. After a main sequence star has run out of fuel, it will either become a red giant or a red supergiant depending on its size. After the fuel at the core of a star runs out, nuclear reactions will start to move outwards, burning the hydrogen that surrounds the core. As a result, the star will start expanding and cooling, becoming much redder. The star will eventually reach about 400 times its original size, thereby becoming a red giant. When this happens with our Sun, it will engulf Earth. Thankfully, this won't happen for another 5 billion years. A high-mass star will go through a slightly different process, resulting in a red supergiant. Due to the huge masses of the stars, once the core collapses after a hydrogen fusion, a higher temperature will occur at the core. This means rapid helium fusion, which will cause the star to become destabilized. A huge amount of energy will cause the outer layers of the star to be pushed outwards, forming a red supergiant. Red supergiants are about 200 to 800 times the radius of our Sun. The Hertzsprung-Russell diagram is a scatter graph which displays the relationship between a star's luminosity and its temperature. The diagram can show how the star's properties change at different parts of its life cycle. For example, red supergiants have some of the highest luminosities, yet some of the lowest surface temperatures. Red giants have similar temperature but lower luminosity, whereas main sequence stars' luminosities and surface temperatures vary significantly. Smaller stars which didn't become red supergiants move on to become a white dwarf. A white dwarf will dispel most of its outer material, creating a planetary nebula, and only the hot core of the star will remain. The core will be extremely hot, as seen on the Hertzsprung-Russell diagram, as some of the hottest stars. The core can exceed 100,000 Kelvin, however it will cool down over the next billion years. If a star is big enough once it runs out of hydrogen and helium, a supernova will occur at its core. A supernova occurs when there is a buildup of mass at the core. Once the core's mass surpasses a certain mass known as the Chandrasekhar limit, the star will begin to implode. The star will heat up, becoming more dense until the implosion bounces off the core, expelling the star's material into space, therefore forming a supernova. For a star to explode causing a supernova, it's estimated that the mass must be about 8 to 15 solar masses. The supernova will leave behind a neutron star, a city-sized object that has the mass of around 1.4 times that of our Sun. Due to the combination of extreme mass and the star's small size, it is incredibly dense, so dense that in fact a single tablespoon would have a mass of 1 billion tons. Due to the large force of gravity from a neutron star's large mass, electrons and protons are squashed so tightly together they combine to make neutrons, thereby giving the name neutron star. A supernova can, however, result in a much more fascinating outcome. If the matter left behind after the supernova exceeds 3 or 4 solar masses, then instead of forming a neutron star, a gravitational singularity will be created. This is a single point containing all the mass of the would-be star. Due to the extreme force of the gravitational pull at a certain point, not even light can escape, therefore forming a black hole. If any object is small enough, a black hole can occur. However, its radius must be smaller than the corresponding Schwarzschild radius of the object. For example, the Earth's radius would have to be below 8.87 times 10 to the minus 3 meters for it to form a black hole.